So my name is Zeeshan Lakhani. Yesterday, Brooklyn on the main track talked about IPVM. I'm going to be talking about our reference implementation of IPVM, how we're trying to really put this into the wild and what we're working on and where we are. So this is Foundations for Open World Compute. My name is Zeeshan Lakhani. I work at Fission as a staff research engineer, and so we will talk a little bit about, in going to build IPVM, what I, also kind of the research and ways that I came across stuff in my mind and how I work. So I work at Fission. We're building essentially open world. I created a thing, I co-founded a thing with some really awesome people called Papers We Love. If anybody's ever heard of it, check it out. We'll be having a conference this year co-located with Strangeloop. And I also attempt to do a PhD at CMU in type theory, specifically a thing called polarized subtyping. So if you're interested in type theory, always down to talk about that. We're in Boston, after all, one of the great programming language cities in the world. And I'm on Blue Sky if people want to find me. That's the new hot thing to do, so why not? Okay, so in framing this, we're going to talk a little bit about IPVM at a glance. Again, maybe people haven't seen Brooke's talk from yesterday or previous talks. I'll do a little update on it, but don't have a lot of time. Want to get to a demo, so we'll just look at it at a glance. We'll talk about workflow systems. Has anybody here ever used Apache Airflow, things like Cadence, Temporal? Have you seen these things in the Web 2.0 world? That's where I've come from. Very new to Web 3. So I'll talk a little bit about research there. We'll talk about with all my friends. So in Brooke's talk yesterday, we're really heavy adopters of Wasm, deterministic Wasm at Fission is what we're really going for on the first build of all this. And we'll talk about WebAssembly interface types and the Wasm Component model, which is kind of where things are going. A lot of this talk will kind of reference what does it mean to say we're trying to build open world compute and interoperate. We're at a conference, obviously, where we've had, Bacliao, we've had other compute teams, and I think I'll showcase some of the differences where we're going with IPVM, especially toward this interoperable model to work with all these other compute groups and others as well. But what are the hard parts? There's a lot of hard parts, a lot of good parts, a lot of hard parts, maybe impossible parts. So how did we get here? Brooklyn yesterday again talked about this. Fission and Brooklyn had been envisioning this interplanetary virtual machine, essentially called interplanetary like this, very akin to IPFS. And obviously there's a bunch of kinship, as we'll talk about there. And so, this idea of a content-addressed compute for the open world. And so when when I first started working this earlier in the year, I'm doing this in very GPT style, because this could have been GPT, but this is Brooklyn's words chatting with me, which is, these are the tenets of IPVM that we have and what we're going to build out. Nothing less than connecting all the world's users and services. Easy, right? That's whatever. That's easy. The HTTP storage and compute equivalent, open, interoperable, and everywhere. Okay, it's a little harder. Everywhere? Okay. And then must be substantially better than Web 2.0. Substantially is a really big word here. Bolded, of course. When I was, these are the motivations. I was like, well, this is going to be a little hard, but let's see what we can do. And so that's what we'll be talking about. So what is IPVM or NIPVM? For people who know IPFS, I'm guessing most of the audience is pretty familiar with it. We know that IPFS is an interplanetary file system protocol, P2P file sharing, leverages content addressing for file identification and verification. IPVM, kind of leaning into this, is Fission's effort to bring computation to IPFS using Wasm, SPKI, System of Public Key Infrastructure, and object capabilities. I won't talk a lot about Ucans in this talk, but a lot of this model that we're developing is around Ucan invocations and how we think about authorization, verification, and capabilities of who can do what and how we kind of build that trust model. We could talk a lot about, obviously you could hit me and Brooklyn up more offline to talk about that. And furthermore, IPVM liberates computation from its dependence on pre-negotiated services and paves the way for interoperability. And I think a key thing that you'll see, as people might ask, what are the differences between IPVM and all these other compute systems, integrated with content addressing IPFS? I think this interoperability maybe is the key word. And the other one that I think is a renewed focus on usability. I think a big thing that we're thinking about in particular is how developers of all types, whether you're working in the browser, the front end, whatever the case might be, how can you leverage this without having to know too much? And as we explore some of the Web 2.0 workflow systems, as I do right now, the complexity is really high when we live in a world where we think a lot about failure, which I do, and I'll talk about that. Okay, so really in the whole goal of this, as Brooke has always said this, IPVM is the long, fabled execution layer. And as she alluded in her talk, it's a multi-tier world. We talk about decentralization, but this is not, don't run it on AWS, don't run it on Google Cloud. This is, run it there. That's a large tier. They can do lots of kinds of work. You can also run it in your home. You can also run it on your phone. That's the world we want to explore, and multi-tier research is like a very ongoing thing, especially I came from a lot of work in networking. And so, this is not one player or one group or anti-big company. This is really having everything work together. So Homestar, for those who may have watched the Flash animation, that's what it's named for, because it's a runner. Logo incoming, still working on it. Most of you get Mid-Journey detailing some concepts. But Homestar is our reference implementation for IPVM, the specs that are out there today in the IPVM working group. Heavy leverage on Wasm, IPFS, the Bytecode Alliance, which also, again, Wasm, but specifically Wasm Time, IPLD, and then Ucans. But the little story I tell as we go into this, again, talking about workflow systems, and people must be familiar with these things, right? Because the one thing is we're not just running functions as a service, that is one part of it, but it's running entire sets of execution. And workflow systems, again, have been around. People are, again, familiar, Apache Airflow maybe. Lots of big companies run workflows, and you might be familiar with these kind of things, like steps, aggregates, the ability to do some pieces in parallel while doing some things that are dependent on each other, separately, on its own task. And so again, the big companies that are out there doing this today, so Cadence is not a company, but it is the system, a workflow engine that's created by Uber, used heavily at Uber, used heavily at DoorDash. So a lot of major companies use Cadence today. And they're essentially like, we have this fault-tolerant stateful code platform where we can focus on your business logic and let Cadence take care of the complexity of distributed systems. And the one thing, as I've been in a lot of talks at this conference, we talk a lot about things working well. I used to work on distributed systems at a company called Basho that had a database called Riak back in the day in the wars of NoSQL, if people remember, or 2015, 14, and beyond. Failure is everywhere. Distributed systems are still hard. It is not a solved problem. And so, it's great to seeing there's companies like, or tools like Cadence, libraries like Cadence, they're like, we'll take care of everything. One that came from the people who did Cadence at Uber, they spun out a company, left Uber and spun out a company, and they called it Temporal. If anyone's heard of this. Their taglines: code smart, move fast, break nothing, eliminate complex error on retry logic, avoid callbacks, and ensure that every workflow you start completes. Temporal delivers durable execution for your services and applications. Cool. That sounds awesome. And then, they're probably like, yeah, we get a lot of money for this, which they do. And they're used today by Datadog. They're used by a major company today. They run their own conferences. And people, when you think of workflow systems, one that's definitely there, and if you have not seen this logo, this is AWS Step Functions. I feel like people have used this maybe or thought about this. This is a quote from a friend of mine, which I've always liked, which is, workflows is YAML, which should be a really bad thing, which I don't know if you ever tried to use step functions. It can do a lot, especially if you're integrated in the AWS environment with all your systems in deploy. But it is, when we talk about usability, I think the big win, interfaces, design, user thinking, AWS is that's one thing, and I'm on record saying this, that's one thing they don't put as much effort into as some of the other things around failure and systems that they've done really well at. Okay, so continuing on workflow things, and I'll bring this in. Usually when I gave a variant of this talk at IPFS thing, I asked this question, but I'll just go to it. But show of hands, who near here is the difference between like idempotence and determinism? 2. Okay, so the definitions are good. Okay, great. Again, I really sparked this because I just told you about these 3 workflow engines, and particularly cadence and temporal. Again, majorly used by all the FANGs and major companies. You have to know what these words are when you work in compute. And people who maybe have done a lot of work in like Kubernetes or other compute systems, these words come up all the time. So idempotence, the property of certain operations that you can do more than once, but get the same result as if you did it once. This came from Pat Helland, if you love reading about immutability and idempotence, and actually he has a great blog post about determinism as well, which is something like to the degree like I'm not deterministic anymore, which is really great. And so what is determinism, right? So this is a definition from an interesting paper on parallel programming, but essentially it's saying many, though not all, transformational computation are deterministic. Definition, a given input is always expected to produce the same output. This category is vast. And so there are times when you're working in compute and you're thinking about a series of functions that you want to run where you might just have something that's just deterministic, just idempotent, or both. And so if you look at these workflow systems, and this is like me, I came from Web 2.0 to apply something to like a Web 3 implementation to this open world compute goal. When I looked at these workflow engines in detail, I felt like, well, everyone's just writing workflows. Everyone's just writing compute. It's easy. You don't have to worry about the hard problems of distributed systems, and yet you have to know all these things. And so, they tell you, and this is from the temporal docs, if you do workflow execution, they must be idempotent deterministic. Well, what if aren't most of our apps making calls to third-party network, calls over the network, and the network, we know that like things fail all the time. Network fails all the time. We get partitioned, right? That sounds hard. And what if I want to deal with things that are definitely not deterministic, like time, random, etc.? Oh, these workflow libraries and clients and SDKs, I have to use their version of random, their version of time. That's cool. Okay, so I have all these libraries. Now you're imagining, so how do these systems work? Some company has to build all the tools. And hopefully you don't do something wrong as a developer. Call services, so there's a concept of activities. This comes from Microsoft. I'll talk about this in a second. But activities, I can make external calls with activities. But activity code, and it can be non-deterministic. But if you look at these again, these are all like from the docs of these companies. They tell you, activities, we recommend that they are idempotent. They just recommend it. You write a workflow code that's not idempotent with as an activity, things can go wrong. You can't get replayability. You can't get incremental. You can't get reusable compute. So they leave it to you. The big point I'm trying to get at, you want to do an open world compute engine, and these are some of the systems, in a more Web 2.0 space on this. They expect you to know idempotence, you to know determinism, and how to work with it. And I think for most people here who've worked with developers, this is hard. So what's going to happen? Everyone's going to mess it up, and we're just going to be like, well, you don't get any of the cool guarantees. Sorry, you don't know enough about determinism. That's really a difficult thing to tell people. And so the people who did temporal and cadence, they all came from Microsoft, and they worked on this. This is a really great paper, actually. Durable functions, semantics for stateful serverless. And if you look in here, they have these same ideas of activities, right? Activities are akin to functions as a service like Lambdas. Orchestration, this ability to work in large workflows, those are things that have to work deterministically. And they have this idea of entities as well. A big reason that a company like Microsoft can put this into practice and have developers who know how to write deterministic code and have all this is they have all the tooling in place. You're going to use something with Azure. You're going to write in C#, and we're going to be able to make sure and hit you over the head with how you're going to program compute. That's not a great story when you want to have an open world compute where I'm like, hey, you compute, you write some Wasm, you do all this. It's very different, right, than in a model where you're working in a large company. So even Stripe actually has a great little talk about using temporal. They use these workflow systems for like petabytes of data at Stripe. And they basically wrapped these workflow engines with their own tooling. Static analysis static analysis, network fencing, testing for idempotency. So they run tests twice, for example. So you want to have that ability to do that. Network fencing is really interesting. So for things that are not activities in temporal, they can make sure you're not going to make a call over the network or call the DB. They even have specific code that you can write about SLAs to fail workflows if you don't hit SLAs. And the one thing in the kind of decentralized space that I don't hear about a lot is people can still have SLAs, right? People still want things to run somewhat efficiently. Those are hard problems that we have to tackle and that we are tackling. A big paper that came through that came to us as we were building this out has been Ambrosia. Brooke talked a little bit about this, which is about providing performant virtual resiliency. And the definition is here, which I think is really great. Provide developers the illusion that machines never fail. I mean, that's awesome, right? Like, I want to live in a world where nothing fails. Everything's healthy. Who lives in this world? Well, if you worked at Microsoft, you can. but the idea that machines never fail by automatically fully healing the system after physical failure, analogous to virtual memory, provides developers the illusion that physical memory never runs out, right? This is great. They actually get around some of this stuff. Ambrosia was not meant for serverless, but they do some really good stuff about how to work with non-determinism. And so they do a thing in Ambrosia called self-RPC. So for things like get time of day or working with random, they'll basically call the node will call itself, store that information, essentially like in a cache, and then do the actual RPC call. So that when you run that thing again, you can get the specific random, or the specific time of day that came, which again is not deterministic. You can get that for that call again, because we want replayability. Why do we want replayability? Incremental compute. For big image processing, stable diffusion, if I don't have to recompute pieces of something, things are more efficient, right? Those are the goals. So I think the whole point of this, as I get to, is we're interested in when things go wrong and what that means for users. And that, I think, is the big difference in what we're thinking about IPVM. We're really thinking about when everything fails, because users have to interact with that. And we want users to have virtual resiliency in mind, that it almost doesn't fail, that it eventually will always work. So the modes that we kind of move into here is replayability. That's a big key. And that's a big key for a lot of these workflow systems I talk about. And IPVM and Homestar essentially is how do we do decentralized workflows and functions as a service. Brooke talked about this a bit, but we're really into managed effects. I won't talk about that in detail, but imagine we want to be able to work with things like mutation at the end of a pipeline. We want to be able to do things like update DNS records. That's to atomicity here, and software transactional memory. We want to be able to update DNS records and make sure that we have to roll back. If something changed, we can roll back. These are these concepts in computing that I don't think they're very hidden, but things that we're used to in normal systems that just become more maximalized when we actually move into having to do this at a large scale, running anywhere and everywhere. Again, those tenets that Brooke mentioned to me in her GPT bot. Capabilities, who can run it? Based on authorization delegation, based on do you have enough GPU to run stable diffusion? Do you have enough CPU? And this really gets into this idea of affinities and matchmaking. I won't go into depth here because of time, but this is where I see a lot of the differences. How can we do a workflow that will combine Bacalhau Docker run for something that Fission hosts, and something that like Fastly. We want to maybe use something from Fastly CDN and their compute on the edge. I want to have a workflow that has all these things in it, and they pass one to the other threaded. How do we do that? Well, that's what we're trying to solve, right? And that's where we think we're solving these things, by thinking about these things up front. So that's the differences in motivation. We heard a lot in this conference. Decentralized service computing platform, computational running jobs. Where IPVM comes in is we want all these things, and we want everybody to play in the playground together. But getting that right is really hard. And then again, this is where we're looking at these, looking at other things like temporal. We looked at Ambrosia, these Microsoft things, because we have to build from these principles. Obviously, a big thing we kind of run into is running into write once, run anywhere with Wasm. That's the dream, right? Java had this dream. If anyone used Java applets back in the day, woo! I used to do a lot of processing. Used to run them in the browser. So that's the dream. It's getting there. It's getting there. And so a big thing that we've been working with, and Brooke talked about this yesterday, is we have essentially an IPLD WebAssembly interface type bidirectional interpreter. But how that really works is we are all into the Wasm interface type Wasm component tooling. We could talk a lot about this offline, but we're essentially all in. You use this tooling. We can run any kind of Wasm within our reference implementation. And the big thing, I think, for people who don't know, like in Web 2.0, for Kubernetes, Wasm Edge, which is a major CNCF player for running edge functions in Wasm, they're moving to WIT as well. And so this is what we're doubling down on. And so the component model, these are definitions from I'll go through them pretty quick, but essentially portable cross-language composition, core tenets around language neutrality, embeddability, optimizability. The whole thing with the component model, which has been reworked many times, and we're still not in the write once, run anywhere. Like it's still like an attempt to make this all work. But the goals of the component model are really like I can write Wasm in any language, compile it to one place, and everybody else can run it. And that's a big part of doing open world compute. And so again, we've written this bidirectional interpreter. That's about 80% done, which takes you from IPLD to WIT. The cool thing that happens here is because it's bidirectional, you now get a lot more types in working with WebAssembly now that you didn't have in IPLD. Right, and that's a really cool thing, I think, is that the only difference is you see here, there's no recursion, right? If you look at this, yeah, there you go, cool. Everything here is like very, there's nothing that's recursive that can call itself, where IPLD is completely recursive. And so making that work is you have to use specific types around like unions and variants and stuff like that WIT gives you. And we have the ability to go back and forth on this. So I think that's a really key going forward. And then we've really adopted this idea they're working with workflows and working with CIDs, the content address data, and IPFS, is that is promise pipelining. So essentially, within a workflow, and I'll show a quick when I get to the demo here in a minute. You just have a SID that you're awaiting. It might be within the workflow itself as a task that you're running, and you're going to await that promise and invoke it. And that can be invoked. You might have to wait from another peer. It might be within your local workflow as well, and we await that, and we essentially use this promise pipelining to make that work. But the difference is where a lot of this work on promise pipelining was about concurrency, we're thinking about this in a distributed way because we're doing this over the network. So it's not concurrency among strangers, but we're distributed among strangers. And so that's the work that referencing there, Mark Miller. And so in our runtime for Homestar, we have this execution graph and scheduler. What you can see here is that you can have a bunch of these WASMs. If they're dependent on each other, as it showcases here, if you can see here with these SIDs, there we go. Right here, you have this first SID that's going to run as part of the first batch, but you might have a second batch that are all dependent on that first one. So we'll run that. We can run those steps in parallel while waiting for the first one to finish. And then we have the concept of receipt. So every time a compute is done, we have a receipt for that computation. And so when we actually schedule this, if we already have a receipt for the bottom computation after doing the analysis for the schedule, I don't have to go back through the rest of it. I already have the answer, right? And I'll show that in the demo in a second. But you can see here, and we actually work with this bottom up for receipts and then top down essentially for execution. And so the way we use receipts as well is we use gossip sub over libp2p to have like a sub mesh of our peers where they all get it. They all get the records and store them essentially in SQLite as a cache. But then we also send it over the network of libp2p for essentially as being a provider and pushing records out and being a provider for receipts if your mesh does not have it or something happened where the cache didn't get it or the cache was released. Okay, so demo. Bear with me as I get the mic up here. Share my screen. Yeah, all right. Let's see if the demo gods work. Can I switch to this? Is this possible? Thank you. All right. I will run some stuff, and we hope it will work. It's very cold in here, so I'm shaking as I'm doing this. Oh, that's always a good thing. All right, that's going to run now. All right. It's Rust, so you have to, the waiting, even though it's incremental, you have to wait for it for a bit. All right, so like every time you want to do this, we have an image processing example. And I'll just zoom in here. So we have two workflows, and these are kind of like workflows, again, you'll see in most workflow systems. And right now, you can imagine just reading JSON for this stuff. But we have a workflow on the left. That's workflow 1 that will do some image processing, rotate an image, blur an image, grayscale an image. We have another workflow. And so the workflows are going to reuse the same 2 effects for the first 2 steps, and then do a different third steps on the image. And we'll show that. All right. So, and you'll see here we have this little workflow 1, workflow 2, right? So we'll start playing this. Let me see if I can double check my, oh, it's working good. Okay, cool. We cropped an image. We rotated an image, and let me see if I can stop this before, I always do this. Let me see if I already finished or not. Oh, I already finished the blur. Actually, that's fine. So if I failed it, I won't do it again, but if I failed it, we'll reuse it. But we'll see this happen in workflow 2, right? So let me go rerun this. So even within failure, it can reuse, or in another workflow. Again, apologies for Rust. This is the one issue with it. As we see here in workflow 2, should reuse the images. Let's see. Oh, hold on. Is it running? Okay, hold on. Sorry about that. All right, that did not work. Demo guys, let's do this one more time. Let's see here. All right, so yeah, you see here that I just reran it again. It uses the same, already had the incremental compute running, right? And so if I run workflow 2, boom. So we see here, let me zoom out a little bit, right? It reused already the computation of the other 2, and then give me the grayscale image, right? You see how fast that can be, because I can just rerun it again. If just to really showcase that, if I do this again, boom, right? And this is the beauty of incremental compute, right? So if I fail and I come back, I already had previous parts of my compute already done. I'll just reuse them, and I can keep running. This incremental compute is key. Replayability is key. Getting replayability to work across task types, that's the hard part, right? If we want to do this in our operation that we've really been talking about. Okay, so just to finish up, go here. Cool. All right, so good, cool. So this is where we're going. We're in the early days, about 4 months in. So what we have right now essentially is a singular runtime that can work with workflows on a local node, work essentially through failure, work with receipts, share this over libp2p, share this over the network, gossip this over the network. What we're working on moving toward is now, we have the serverless part, but obviously a big part of Fission, again, usability is working in the browser. So we want to have the ability where you can run the same edge function on the edge or in the browser, and I guess the browser is a kind of edge, right? Anyway. Bootstrapping and coordination. So a big part of where we're going is matchmaking. Again, to interoperate with other groups running Docker, running this, running that. We want to bootstrap. Do you have the GPU? Do you have the CPU? Do you have the key if you want to work with private data? So we have this kind of separation between a compute node that you're actually running operations versus coordination. There will be nodes in our system that just know how to coordinate and be like, that data that's closest to the we're compute over data, right? That has a bunch of petabytes of data. Let's move the compute over there. But I think a big thing of IPVM too, we're looking at it in both ways. It's about, hey, a big piece of data is over there, move the compute. But we can also move the data around if it's not that big too. Like we can do a lot of this kind of stuff, right? We can think about this in a kind of push-pull way. We're going to be, a big part that, again, I didn't really get a chance to dive into manage effects, but we have we want to have the ability to work with effects. This is like HTTP calls, DNS, our own random number generation, but having to do it without forcing the user to like have to know all this. This should just work under the hood. And then I think a big part, as I heard in one of the talks earlier from yesterday, is we don't want people, as we have our runtime and we have our nodes and we have our libraries, we don't want people to have to always give us PRs or fork stuff and run it. That's like the worst, right? So we are thinking through heavily on like the plugin system to do this, and Wasm is a great deal on this. And so if you want to work with effects, you can actually drop a lot through WASI. I didn't really talk a lot about WASI, but that's essentially a way to work with stuff on the operating system at the host level. So you can ask me or Brooklyn for more. I won't go through all these components, but we've really architected, again, thinking from these higher level views on how we wanted to do this. And where we're really going, again, is open world compute. And I hope you will join us. Because to actually make a usable system for people to run compute everywhere, substantially better than we've had it, we need everybody together. Better together. Thank you. What data supports incrementability, replayability better? Yeah, I mean, I think obviously, I mean, even from that demo, I mean, image processing is a great one. Any processing like this is really great, I think. But of course, you know, again, when you look at systems like all the durable function, durable task stuff, that replayability is a big part of what they do. And so, what are the things that Microsoft / people are doing? So. In Datadog, for example, which uses temporal, they use replayability because if I already formed a large aggregate set of data, why would I ever recompute that again? And you're talking about they're forming large aggregates of like monitoring data or doing samples over large swaths of metrics, for example. That's like one example. So to me, it's like I think, replayability is key. The incremental compute is key. I mean, there's two reasons. One is obviously on the brink of failure. Of course, if I've already done a bunch of compute tasks that took a long time in an eventual world, then of course, if I went offline and I come back online where if I can't compute it locally, obviously we think a lot about local first thing. What can I compute locally? But if I can't compute that locally, I have to do something because I don't have the GPU or the CPU to do it. Then, finishing 4 steps of a 5-step workflow and just coming back to do the 5th step is really important, really key. But of course, it's I think like I showed in the workflow too in that demo. If somebody's already done a bunch of like aggregate work, I can just pipe in and use that and do my unique differences afterward, right? So if you think of it like in I used to do a lot of work in observability pipeline stuff, right? So I've already done, somebody already did 10 steps on an observable, like some data pipeline, and now I just want to like compute that data with a different feature. Or something like this, I can just go, I already have the pipeline of that. I'm just going to consume that last piece and then do something unique with it. So I think that's where the incremental obviously comes in for so many things. Yeah, I would say the incremental part is not new to IPVM. I just think content addressing gives us that out of the box where if you look at temporal cadence, you essentially have to run a separate server that saves safe state at every step. So that's a big IPFS one. Yeah. 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 That's right. That's a great question, actually. So how do you verify that the previous steps were correct? I mean, so from the one key on the result is that being content addressed, that's essentially like tied to the content itself that ran. Now we have this concept, of course, of promised pipelines. Like parts of pipelines can either be direct data that are inlined or things that I have to wait for on the network. And so even when you say let's reuse that content, well, there's a difference between when it's inlined and when it's so even when you've gotten something over the network and you've inlined it, that's different than waiting for that content address to fill, right? So there's two. So we actually have in the system that as we're building it, we have to look at both. Is this the finished version of the inline version, or the weighted version of the inline version? How do you know it's right or not? Obviously, right now our goals are toward deterministic Wasm, so we can, with that task type, we can do that. We have like the general view that tasks will have to have specs to them and how they work. So I say the one open world, almost impossible hard part that Brooke and I go back and forth all the time, though, is if you tell me you have another, maybe it's not Wasm, it's something else, and you're like, it's deterministic, I promise you this. And so if you've run it, don't worry. You can't trust people, and not that they're malicious. And you could do things like, somebody gave me somebody did receipts that were based on functions that were wrong or not done correctly, and you can slash them. But the thing is, it's like for most developers, right? And when you see this in these workflow systems, they meant to be deterministic, but they used random from the system, right? So how do you work on this? So a few things. So the Ambrosia paper talks about something that we're probably going to have to implement is doing that self-RPC-like thing, so the ability to run some of that compute just to yourself to store that and store that piece in time. But this is the hard part in open world compute, right? Because you can't trust annotation. So somebody actually told me at Microsoft for durable functions when they had C# bindings, they would have it in the first versions of it. People can annotate something as being deterministic or monotonic, for example, as a thing, and then they would use that hint in how they scheduled the compute, and it would blow up. So these are hard problems everywhere at the largest of companies, right? Because developers sometimes just don't know. So as much as you can do documentation this, but we have a grid. I don't show it here of like what are the main tenets of things: determinism, idempotency, or what becomes pure, what's impure, what can be managed and mutated at the end. We think by having a very limited subset of the kind of tasks that you can do and what you affiliate with for that task will be really key. I think the eventual goal will be tooling, though. I think that's what I've seen, like what Stripe has done, for example, with temporal, is essentially if we in the community can offer tools where when you build a task or you build a plugin, we can actually check for those things. We also have some ideas. One thing with Wasm as well. We can do some analysis on the Wasm because that's a great part of it as bytecode. And we could do some ahead of time work as well there. So it's really a tooling system, and that's also a big part of like open world compute. Cool. Thank you.